Okay, hi everyone. Good morning. Somehow we only have 2 weeks before Thanksgiving break and 2 more weeks after Thanksgiving break, which seems like all of a sudden the semester is almost over, which is crazy. Okay, so let's see. We are, make sure I'm on the right audio thing. Okay. We were doing double integrals last time, and now I want to talk about triple integrals. Let me just, well, there's this handout I'm going to put on the screen. So there's a handout for today on the handouts page of Blackboard. But I do want to sort of motivate this a little bit by the one dimension down case, because that's what we always seem to do, right? So let's talk about triple integrals. Go down a dimension first. I think I sort of mentioned this maybe last week sometime, but if we have, some sort of a single integral can actually be thought of as a double integral. Let me just give some examples. So like we had something like that, and then we have another function like that. So let's say this is y equals f of x, and this is y equals g of x. And we want to integrate from, let's say this is x equals a. Let's just pick up a point over here. X equals b. So this is our region, right? The area of R, we sort of know from single variable calculus, right? The area of R is the integral from a to b of what? F of x minus g of x dx. Got a bunch of little Riemann sum rectangles, and each one of them is the difference in the heights, right? But I think now that we've thought about life in terms of double integrals, we could rewrite this the following way. I could say this is actually the same thing as this double integral right here. 1 dy dx. So that's right, because if you integrate 1 with respect to y, you get y. And you plug in the endpoints, you get f of x minus g of x. So do you agree with me that this inside integral is actually just f of x minus g of x? Right. So we can rewrite a single integral as a double integral. And in fact, maybe we should have been doing this all along or something. That somehow an area really should be a double integral rather than, so I mean, this, if you think about it, this really just is, if I rewrite this as the integral over of R of 1 dA, right? We sort of said that that's the area of the region and that these are the same thing. Right, it's just how I set up the region. Okay. So a couple things about this before we go up a dimension. The first thing is like, how do we know the bounds? So the bounds, I mean, we have the function on the top and the function on the bottom. We also have this left and right endpoint. And that's all sort of specified. You could say it's specified. But I could have said something like, this is the region bounded by y equals f of x y equals g of x, and x equals b, right? I could just provide you that information. And so how did we find A? How would you find A in this case? Yeah, Leo. Yeah, you just set f of x equals g of x, right? So the bounds, or so the x bounds of the integral come from either vertical lines, here x equals b, or intersections of curves, which in this case gives you the x equals a, right? I just want to make this point because when we go up a dimension, there's going to be something very similar. And I just want to sort of point that out. If you say something like, if I just give you the functions, the curves bounding the region, then if you have a vertical line, then yeah, that's one of the bounds. If you have a horizontal, I mean, if you have the other way to find the intersection, the other way to find the bounds of the region is to intersect the two curves. And so, just again, this is all going to seem kind of silly, but just it's going to make more sense when we go up a dimension. We can think of the interval from A to B as the shadow of R on the x-axis. Meaning if we shine a light from above, above, right? If we shined a light from way above and we look down, we would just see, all we would see is the interval from A to B. Like if you put your face in the plane of the blackboard about a mile up, because the blackboard keeps going forever. It's a magical blackboard. And you look down, you're just going to see the interval from A to B, right? This all seems kind of maybe a little bit overwrought, but it's going to be very important when we try to go up dimensions. So now let's go back up a dimension. Go up a dimension. So say we have some region in space bounded by some surfaces. Right? And I want to find the volume of that region. Bless you. Now suppose we have region in space. I'll give you an example in a second. Actually, I think there's an example at the bottom of the screen there. So let's just do this example while we go along with this. So z equals x squared, y plus z equals 10, y equals 0. So that's an example of a region in space bounded by some surfaces, right? We can actually visualize this. Let me just share the screen for a moment just to say, this is the handout for today. On the handouts page, and this is the example I'm looking at. Now I actually have some Mathematica code here to visualize this. Let's take a look at this. So okay, you share Mathematica. Let's do 200%. Okay, so here is if we actually plot these surfaces. Let's see what we get. You can do it. Oh, rainbow circle of death. Let's wait a minute. Okay. So z equals x squared is this parabolic cylinder, right? The parabola sort of moving back and forth. Y plus z equals 10 is that tilted plane. And y equals 0 is that vertical plane. You see that there's sort of a region inside there, like a space region. You can actually use inequalities. There's some nice mathematical commands to use inequalities to actually get it exactly. It's this thing right here. Cool. Okay, so if you look at, so I want to think about the analog with what we were just doing on the board, where there's sort of like a top surface. We had a top and a bottom function when we were doing that area, right? Now we have a top and bottom surface. So this like plane is the top. This curved parabolic cylinder is the bottom. There's a shadow. I think I have X and Y switched. If I want to look like directly from above. Wait, something is wrong. I have Y pointing downward now. I'm trying to look at the axes on this side of the screen. Okay, so X is from, X is from -4 to 4, and Y is from 0 to 10. Okay, so there is a shadow, right? If we look from above, there's some shadow this would make in the XY plane. In fact, we'll talk about how to find the shadow in a moment, but here's what it, whoa, hello. Here's what it looks, here's what it looks like, or here's what the shadow actually looks like this, right? Sort of believable. The idea is going to be to figure all this out without having a program graph everything in 3D for you. But let's just think about what's going on. So if we want the volume of this region, let me just go back to let's just think about if we want the volume of this region, right? By the way, somehow the book and I guess me like to use R for two-dimensional areas, two-dimensional regions, and W for three-dimensional regions. I don't know why. So W is what we're going to call this region in space. So it's like find the volume of W. Well, the volume equals the triple integral over W of 1 dV, we want to say. That's kind of like the dumb answer, or like the empty answer, which is we think of this as the integral over the whole region of just 1, right? The function 1. So just like we did with areas, we can think of an area as a double integral of the function 1. We can think of this is the triple integral of 1. So, but the real question is, how do we set it up, right? That's how do you set it up as a triple integral? And the idea is you look at the shadow. So I'll say, okay, but how do we set up? Set up the integral over W. That's supposed to say right there, because it should be a setup. And I'll put the handout back on screen just because you can see it here too. Right, this is adding up these are adding up little patches of volume. Just like we had little patches of area before in the 2D picture. Now we have dV is a little patch of volume. It's a little tiny cube or volume. And we just add them up over the whole region in space and we get the total volume, right? But how do we set this up? Well, similarly to the area of a region, we look for, I guess, 1 or A, the sort of top surface. B, the bottom surface, and C, the shadow of W in the XY plane. Right? And so then if we find all that, then we have something like what's on the handout there, is that you basically do the integral over the shadow as the outside is actually an outside double integral, and then you have the integral of from the top to the bottom, or from the bottom to the top inside. So let me just write this in general, and then we can look at this example. So then the volume of W is the integral over the shadow R of the integral from Z equals, I guess I was going to call this like F top and F bottom, the top and bottom surfaces. Z equals F bottom, Z equals F top of 1 dz and then dA. And then if we identify the shadow, we've reduced it to a solved problem. We reduced it to just finding the double integral over the shadow. Okay, so let's think about this. Let's think about this example. So in the example, we have z equals x squared, we have y plus z equals 10, and we have y equals 0. Okay, so, well, if we look at the Mathematica picture, what was the bottom? The bottom was pretty easy to identify. The z equals x squared is the bottom, right? Yeah, so in this example, well, I'll sort of show you how we can see it this way, but I'll also try to think about how we could see it without having the graphs in front of us. Z equals x squared is the bottom, i.e. the f sub bottom of x comma y is x squared. And what's the top? We have two other choices, right? So is it the y equals 0, or is it the y plus z equals 10? Yeah, it's this tilted plane seems to be the top, right? Y plus z equals 10. But really what that means is we want to solve. It's like z equals 10 minus y is the top. Fair? So it's really the function z equals 10 minus y, which is the top. And now what about the shadow? Well, what makes up the shadow? The shadow seems to look like this. And like we said, if we, sorry, let me just share screen again briefly. So the shadow is this. How do we find the boundaries of the shadow? And if you look back at how we found the interval to integrate over in the dimension down, how did we do that? Yeah. Yeah, so the shadow, so part is from where F top intersects F bottom, right? So here, if we did that, we could set the z's equal to each other. In the example, sorry, let me do it this way. So in the example, z equals x squared equals 10 minus y. So you could say y equals 10 minus x squared forms part of the boundary of the shadow, which in fact, if you look at that on the screen, it does look like an upside down parabola, right? And in fact, you see it here. And you can see x squared plus y equals 10. That came from intersecting the two, right? But that's not the whole shadow. Where's the rest of the shadow? What forms the rest of the shadow? Yeah. Y equals 0. That's the third surface. We haven't used it yet. And it's vertical with respect to it's sort of parallel to the z-axis, right? It's vertical with respect to the xy plane. So the other part comes from, go back and forth between. The other part comes from what I would call like vertical walls. So actually, if you think about it equation-wise, if you look at those three equations we had, two of them had a z in it, right? Two of the equations had z's in them. And those were the ones that involved the top and bottom surface. One equation doesn't have a z in it. And that means it's sort of vertical, right? Because z could be anything. But it's just the equation y equals 0. So it's vertical in the xyz space. Therefore, that actually forms a boundary of the region, so a boundary of the shadow also, right? Just like I was saying in the example with in down a dimension. This was this formed part of the shadow, and this x equals a and x equals b. This is the picture I had on the board earlier. I think it's maybe on screen, zoom barely. So this came from just deciding that this was one side of the region, right? Sort of exact, so it's totally analogous to that. So here, vertical in XYZ means there should not be a Z. Vertical in XYZ space. Just like here, vertical in the XY plane means there's no Y in the equation. X equals constant is a vertical, right? So vertical XYZ space means no Z in the equation. So here, y equals 0. Okay, so those two things form the shadow, form the boundary of the shadow, those two curves. And so now we can pretty much start to write this down, because we can draw the shadow. Yeah, in this example that we have, I was sort of trying to give general principles, but let's do it in the case of this example. So in our example, the volume of W is the integral over W of this dV, which is the integral over R. And then the integral, we identified the bottom and the top, right? Z equals x squared was the bottom. Z equals 10 minus y is the top of dz dA, where R is the shadow, is the region bounded by y equals 10 minus x squared and y equals 0 from that, right? I'm just sort of recapping what we said there. And like we just said, that's actually, we can draw that pretty easily. The shadow there, it's something like that. Y equals 10 minus x squared, y equals 0. And so this thing right here is R. And that's not hard to set up, right? So really we can say, like, let's just set that up quickly now. Now you're experts in this. We can do this with, actually, if we want to do this with vertical slices, we do need to find these two intersection points, right? What are these points? What's the x value there? Not the nicest x value in the world. Square root of 10, right? You just set this equal to 0. So that's the square root of 10. That's negative the square root of 10. The bottom is y equals 0. The top is y equals 10 minus x squared. So if we wanted to write this all out as a triple integral, we would have z equals x squared, z equals 10 minus y on the inside integral. The middle integral would be y equals 0 to y equals 10 minus x squared. That's dy. And then x equals negative root 10 to x equals positive root 10. And that's dx. Yeah, Alex. Oh, y equals 0 is the x-axis. This still is the y-axis. Sorry, I was just explicitly writing the equations. Yeah. Good. So, I mean, it's a lot, but this is now something you could integrate and actually find the value of, right? Does that make sense? Yeah, Caleb.
What made you basically set the parameters for the interval? What dictated the order?
Yeah, so, and this is good. This is going to come up later. So it turned out that this had a nice shadow in the XY plane. This figure. That if we look at this, it has a nice shadow in the XY plane. So in that case, we had a top and a bottom surface, and then the shadow in the XY plane, right? But you could imagine, like in this example over here, I could imagine a different region in the plane that's more like this, right? And if you wanted to find the area of this region, well, the traditional single variable calculus way, you'd want to do top minus bottom, but there's two different bottom curves here, so you'd almost have to break it up into two separate integrals. But if you look at it from this perspective, there's a y top and a y bottom, because these are like x equals f of y and x equals g of y. So you could do top minus bottom. So the shadow there is sort of nicer in the sense of being like not caused by two different curves or something like that. So we're going to see examples where it's actually better to project onto the YZ plane or the XZ plane or something. And so, yeah, going back to this. Right, in fact, here, if you wanted the shadow on, say, the XZ plane, ooh, if I make X, nope, this is YZ. And I just made Y. I don't know what I'm doing. Trying to make Y horizontal and Z vertical. These Z's move around depending on where. The Z keeps bouncing back over and over. So you could look at the shadow in the YZ plane if you wanted. Or you could look at the shadow in the XZ plane. Can I do that? Something like this. Yeah, this is the shadow in the XZ plane. If we look at it from this direction, because now I have X horizontally and z vertically. So whichever way you look at it, like whichever shadow you look at, the inside integral is the one that's like the other variable. Like because here in this example we projected onto the xy plane. So z equals were the functions inside, and we had dz here. And then the shadow is dx dy or dy dx.
The shadows of what we were doing.
Before, yeah. Yeah, so that's the thing. This is no different really than what we were doing before. We just have something more complicated inside. And we were doing integrals of functions. I mean, it's just a different function. So no, this is a good point. So like what dictated the order, yeah, there's really 6 possible orders here. Dx, dy, dz, dx, dz, dy, dy, dx, dz, dy, dz, dx, dz, dx, dy, dz, dy, dx, right? And so you actually can set this integral up 6 different ways. In fact, I think on the handout, I have that at the end of the handout, like set it up all 6 different ways and see that you get the same answer every time. Yeah, it's my idea of a Friday night. Okay. So you could actually do this and set it all up and see that you get the same thing. So you could actually set it up 6 different ways, and that's just tracking what I'm doing. So the fact that it's dy dx and not dx dy comes from the fact that we use vertical slices. But if we did this with horizontal slices, we would have had dx dy. And the dz comes from the shadow, comes from projecting onto the xy plane, yeah. Yeah, that's right. That's right, so we can do quadruple integrals next. The rest of the semesters, next, later this week we'll do quadruple integrals, next week we'll do quintuple integrals. Week after Thanksgiving, we'll do sextuple integrals. We're gonna try to get to octuple integrals by the end of the semester. No, that's not what we're doing the rest of the semester. That'd be insane. But it's kind of fun to think about. So, by the way, should we just evaluate this real fast just to see what it's like? So we're gonna work our way inside out. And so, I guess I should just call this V for volume. So V is the integral from -√10, x equals -√10. Again, most books and examples you see do not state these very explicitly, so it even looks kind of crazier because it's just like the integral from x squared to 10 minus y, the integral from 0 to 10 minus x squared, the integral from -√10 to +√10. But I try to write them out. And so the inside integral is easy because dz just becomes 1. By the way, I could put a function in here. If I wanted to measure like a temperature function over this region and find something about like an average temperature over that region in space, you could put a function in here, it's fine. We're gonna talk about that, but you can do, actually triple integrals where there's a function inside, but it's just easier to think about in terms of volumes. So when we integrate this, we just get z. So we get 10 minus y minus x squared, right? Because that's what this integral right here is just equal to that. It's just z from those 2 endpoints, right? And then if we do the inside integral, again, now the middle integral is the one that's inside. So we get the integral from x equals -√10 to x equals +√10. Now we're actually going to integrate with respect to y. So 10 becomes 10y, y becomes 1/2 y squared, x squared becomes x squared y. And now here's where it gets a little bit hairy. Y equals 0 to y equals 10 minus x squared. And then all of that is dx. Sometimes I separate these things out and just do them separately and plug them back in. I'm trying to do it as one long chain of equalities, but it's maybe not the brightest thing to do. So let's just actually work out what this is before we move on. So, oh my God, okay, so this is 10. Oh, this is gonna be unpleasant. It's funny, so much of the time I just ask you guys to set these things up and not actually find them. minus x squared times 10 minus x squared. Minus, so that was the first part. Oh, then just 0. Actually, it's just 0, isn't it? Minus 0. Let's plug it in y. There's a y in all of these. So plug it in y equals 0. Just 0. Oh, there's something interesting here. I'm going to try to be somewhat clever. So there's a 10 times 10 minus x squared minus an x squared times 10 minus x squared. So that's actually, I could factor that out. This is me trying to be too clever, probably. 10 minus x squared squared minus a half of 10 minus x squared squared. So that's just a half of 10 minus x squared squared. Okay, this is a half 100 minus 20x squared plus x to the 4th. I don't know. I'm just kind of going through this quickly because I don't really care about the answer, but you can check me and make sure I'm not messing up. I guess one thing you could say is, okay, we have something that we could probably put inside a rectangular box that's 10 by 8 by 10 or something. So probably our answer should be less than 800. You know, like you just as a crude estimate, the box that box that I'm actually in the picture on screen. Sure. Okay. Sorry, let me just finish this off. Okay, so the volume equals the integral from minus root 10 to plus root 10 of 50 minus 10x squared plus 1/2 x to the 4th dx. Are people checking me? You should be doing this on your own and not trusting what I'm writing down. Like none of you really should be looking at the board. You should just be writing it all out yourself. See if you're getting the same thing. $50x minus. Oh yeah. Oh great. This is actually symmetric, so I could do twice 0 to root 10 if I wanted to. But you get the idea, right? It's 50 times root 10. 10 root 10 cubed is 10 root 10. So that's minus 100 thirds root 10. Root 10 to the 5th is 100 root 10. So that's plus 10 root 10. And then you're going to get minus the same thing. Because all of these are going to pick up minus signs, but there's another minus there. So really just doubling this. So that's 60. 60 is 180 thirds minus 180 thirds. 160 thirds root 10, something like that. You can check me. I don't know. I don't care. Is that less than, that's a lot less than 800. Yeah. Root 10 is only a little bigger than 3, so it's only a little bigger than 160. Okay, sorry. I don't know. That was a lot of, that was just a lot of algebra. That's really not interesting. But yeah, most of the time on tests and stuff, I'll just be like, set up, but do not evaluate. But if you want to do this all 6 ways, so you get the same answer every time. Did I mess up anywhere? Has anybody caught me? I probably messed up somewhere. Perfect. Perfect. Okay, so it's something like that. But it's possible. It's doable, right? It's ugly, but then you can get a number at the end. Okay. Okay, let's see. There's 13 minutes left in class. So, oh yeah, so if you look at the handout, number 1 sort of goes through all this stuff we just did. So get hit of the shadow in the XY plane if we shine a light from far above. what creates the shadow? There are two possibilities: vertical sides of W and curves where the top and bottom surfaces intersect. So that's what we found here. Which gives us, so we found the boundary of the shadow. Oh, yeah, here's the thing. I showed you in Mathematica what the picture looked like. But what if we didn't have, what if you were just trying to do this by hand? What if you're doing this 50 years ago? Right, when people didn't have Mathematica to play with. The only thing that we would really sort of need is the top and which to identify which one's on top and which one's on the bottom. Right, so just to go back to this, let me just write the equations again so we remind, just to see what we actually had. Sorry. Keep going back and forth between. If you're watching the Zoom, just pull up the handout so you can see this also. Okay, so yeah, the only thing that's really still there that the only thing we really needed Mathematica for is we sort of verified we got the same shadow, right? Just by sort of intersecting the two Z. We basically solved for Z. We found like, so without visualization software, to assist, the point is that we had, let's see, we had Z equals X squared, Y plus Z equals 10, Y equals 0, right? So notice that we can, there's two Z's. The two Z's solve for Z to get the two functions. To get the two surfaces which form the top and bottom. If there was a third Z in here, this would get more complicated. I mean, you'd have to, that's why sometimes you want to look, if you want to think about which shadow to do, like it's a little bit easier if there's exactly two of one variable, because one will be the top surface, one will be the bottom surface. If there's three of one variable, it might be the kind of thing where two different surfaces form the top surface, another one forms the bottom, and it might be better to project some other way. Two surfaces. So here it's, we just said it was Z equals X squared and Z equals 10 minus Y. Now the question, and then the shadow, actually here. So the shadow, like we said, vertical walls, Y equals 0, and intersect Z's. What we did on, I'm sort of just recapping. So X squared equals 10 minus Y. At this point, you can draw the shadow. And I claim knowing the shadow will actually help us figure out which is the top surface and which is the bottom without pictures. So we drew the shadow and we got something that looked like this, right? And this was 10. And this is root 10. And this was minus root 10. Now here's the thing. Which is the top and which is the bottom? Well, here's a way to find out. Take a point in the shadow and plug it into both Z's. Take a point in the shadow, plug into both of these equations, see which number is larger, because that's the one that's going to be on top, whichever number is louder. So to identify the top and bottom, pick a point in the shadow. Let's just say something like, I don't know, 0,2. Plug into both Z's. And then see which is larger. And that will be the top surface. So here, Z equals X squared equals 0 in this case. Z equals 10 minus Y equals 8 in that case. 8 is bigger than 0 last time I checked. So that means 10 minus Y 8 greater than 0. So z equals 10 minus y is the top, and z equals x squared is the bottom, which is what we saw. It is what we saw in the pictures, right? But that's the stuff that we've identified, you know. These are the sort of important things here, like just from doing the analysis without pictures. Does that make sense? So yeah, so if you look at this handout, like these are kind of the ideas. Yeah, so part D, 1D on the handout is basically saying the exact same thing we just did. Pick any one on top and pick any point in the shadow, plug it into both equations, see which gives the bigger z. And then you have all the information you need to set up the triple integral. Okay. So let's do one more of these without, let's just quickly, or do you want to project this a different way? Which one do you want to do? You want to do a new problem, or do you want to project the old problem onto a different plane? New problem? Okay. So let's look at number 2, and then I think, you know, Wednesday we'll come in and we'll just jump right into group work. But let's look at number 2 briefly. That one is not too bad. In fact, you could actually probably predict, probably guess what's happening here, because z equals x squared plus y squared is an upward facing bowl. Z equals 18 minus x squared minus y squared is a downward facing bowl, starting from height 18. So they're just going to intersect. Okay, so let's just do another. This is not a bad example because it's pretty easy. But we only have 6 minutes left, so maybe it's a good example to do. So z equals x squared plus y squared. Z equals 18 minus x squared minus y squared. So here there's 2 z equal equations immediately. So one's top and one's the bottom. One is on top, one is on the bottom. You could probably guess which is which already, but let's do it the same way we did that last problem. The shadow. Are there any vertical walls in this example? No, there's z's in both equations, so no vertical walls. But we intersect the z's, and we get x squared plus y squared equals 18 minus x squared minus y squared. And if you rearrange this, pretty sure you'll see you get 2x squared plus 2y squared equals 18. So you get x squared plus y squared equals 9. So that's a circle of radius 3, right? So this is our R right here. That's our shadow. And yeah, there's an upward facing bowl, a downward facing bowl, and they basically intersect. It basically makes like an Easter egg. One of those plastic Easter eggs you open them. Okay, so that's the shadow. What about the top and bottom? Well, 0, 0 is in the shadow. Zero, 0 is in the shadow. So if we plug in, we get 0 for the first one, 18 for the second one. So this is the top, and this is the bottom. Which makes sense, right? Like again, it's, but just a way to double check. And so the volume is, well, we can sort of start and say it's the integral over the shadow, the integral from the bottom to the top. dz dA. Still thinking about this outside one as a double integral. And now it's just a matter of setting up the shadow, which we could do with vertical or, actually, we're gonna learn double integrals on polar coordinates, which is what this would naturally be, but since we haven't done that yet, let's just do the shadow. Yeah, so my point here though is that you don't really need to be able to like plot the surfaces to do a lot of this. You just have to start intersecting things and try to figure out where to project, you know, like which plane to project onto and look at the shadow, stuff like that. So the shadow, if we did vertical slices, so doesn't really matter that much, but that's 3, that's -3. What's the top? I need a y equals here and a y equals here. What's the top of the circle? Well, the top's a curve, right? So we have the equation x squared plus y squared equals 9. So if I solve that for y, what do I get? Yeah, you get the square root of 9 minus x squared here, and you get negative. So it's a plus or minus. And so, and then the slices go from x equals -3 to x equals 3. So the volume is the integral from x equals -3, x equals 3, y equals -√9 minus x squared, y equals +√9 minus x squared, integral z equals x squared plus y squared, z equals 18 minus x squared minus y squared, dz, dy, dx. I'm just reading them outward, going outward. Zyx going away from the center. And so that's not too bad, I think. Okay. Okay, just think about the outside two being the shadow of just that circle, and then the bottom and the top function surface. Good, and then on, like I said, on Wednesday, we'll come in and just jump right into these group work problems. And sometimes you might try to think about what's the best shadow. Although I think all of them could be projected on the XY plane. So, all right, sound good? It's a party. Triple integrals are a party, you guys. Go do that first one the other 5 ways. See that you get 180 over 3 root 10. No better fun. All right, I'm going to stop recording.